just going to post the link on our website, and we'll be ready to go. Insert, embed. There we go. Okay, let's get started then. So yesterday we started looking at some radicals, and I want to talk a little bit about just some of the applications of using radicals. Can everyone see the screen? Okay, are we good on that front? Yeah. Okay. Just want to make sure my stream is looking healthy. Okay. So I want to take a look at this example here. One of the big things that radicals come up in is using the Pythagorean theorem. So what I want us to do, I want us to try doing a three-dimensional. This is what I like to call it, the three-dimensional Pythagorean theorem. Pythagorean theorem. Okay. So let's do an example of the three-dimensional Pythagorean theorem. So let's start off just by reminding ourselves what the Pythagorean theorem looks like, and that would be something like this. So we would have with a right angle triangle, we would have A, B, and C, and the Pythagorean theorem talks about the relationship between these sides, and that relationship is that A squared plus B squared is equal to C squared. Or we can kind of, like we have three different variables here, all of which we can solve for. So we could solve for A. In this case, A would be equal to the square root of C squared minus B squared, right? We can solve for B. B is equal to the square root of C squared minus A squared. We can solve for C as well. C is equal to the square root of A squared plus B squared. So you can already start to see that the Pythagorean theorem is going to be a great source of applications for radicals, because just by nature of the formula, we get all sorts of radicals. Yes, I'm online now. Someone's just asking if we have class right now. Okay, so yeah, looks like we've got a few people online right now. And anyone on YouTube? Looks like we got one person on YouTube right now. I think I'm on YouTube. Let me copy this. Yeah, I'm on YouTube. I wonder if maybe my website didn't publish properly. Yeah, it looks like my website should have the link to the YouTube stream. I put it on Discord now. So yeah, I mean, I think I'm on YouTube. YouTube isn't telling me that I'm not live. I've got a countdown timer, and oh, it looks now I've got 5 viewers on YouTube. So yeah, YouTube should be working. Anyway, back to the Pythagorean theorem. So this is the sort of like the two-dimensional version of it. I'll just sort of that's not actually what we call it. I'm just kind of making up these terms, but this is what I like to call it. So you could think of this as the two-dimensional Pythagorean theorem, right? Because it's only two-dimensional, like it's a flat right-angle triangle. But the three-dimensional Pythagorean theorem is a little bit different. So let's see if we can solve for the given diagonal. So I want to find the length of this given diagonal here. Okay, so I'm gonna make a box. Okay, a three-dimensional box. So here's the front of my box, and here is actually, you know what? This looks kind of like a square, so I'm gonna make it purposefully not a square. So this is definitely a rectangle. Okay, so here's the face of my box, and then I'm going to have the sides of the box like this, and then we've got X-ray vision, so I can do something like this, right? So we can see through the box like that. Okay, so there's my box, and I want to find the diagonal from this corner to the opposite corner over here. So again, because we're kind of looking inside the box, this is sort of like an X-ray vision sort of thing. So I want to find what is the diagonal of that line. So from one corner to another. And I should also point out that we should have these measurements. And let's say that this is 1, 2, 3. Let's say that this is 4. Let's say that this is 3. And let's actually give these. Let's say that this is 4 meters and this is 3 meters. And then let's say that this one over here is 2 meters. Okay. So there's several ways of tackling this type of problem. One way is to do it directly. There is a formula. Like there is like the formula for like a 3-dimensional Pythagorean theorem. I could just give you the formula and we'd be done. But I think it'd be more fun if we actually just tried to solve it using the tools that we already know. So I think that the main problem is that we don't have, it looks like we don't have enough information. But what I want to point out is that, like, if we sort of kind of drew a line like from here to here, and maybe I should make it a dotted line because it's, again, sort of see-through. So if I did this, then all of a sudden maybe you can see that we have a right angle triangle here, and I'll copy it over here. So the right angle triangle would look like this. Okay, so so this side right here, maybe I'll choose a different color just so we can really see what's going on here. So this side right here is this side right here, okay? And the actual diagonal that we're looking for, let's choose maybe purple. Let's do purple. So this diagonal right here is this diagonal right here, okay? And this the bottom line, which is still blue, that's the bottom line. So this is actually a right angle because well, this like the yellow line goes straight up and down, and then the bottom blue line is perfectly flat. So they do meet each other at right angles. So we can sort of extract a right angle triangle from this diagram, and that should probably help us. So keep in mind, this is what we're looking for. We want to know, this length. Okay? We want to know this length. And we should probably hope that at some point we're going to need to use all of these numbers in our calculation. Like we should be using 3 meters, 4 meters, and 2 meters in our calculation, because you can imagine that if any of those values change, then that would affect the length of this diagonal, right? So we are going to have to use all of those at some point. But for this first stage of the question, we don't actually need to calculate that. All we would do is just, we'll take the diagonal. So I know that, like if I'm trying to find out what this side is here, let's draw an overhead view. So we'll do an overhead view. And that would give us the, let me just grab this red. So this is the overhead view like this. And this blue line is going from one corner to the other. And we can calculate that. We can calculate that because I know that this side right over here is 2 meters. And this side over here is 4 meters, right? Because I'm looking like from above, so I don't see any height. It's all just flattened down. So now I can actually go ahead and calculate the blue line, the length of this blue line, which is this line right there. So it's going to be, let's call this length b. So b is equal to the square root of 2 squared plus 4 squared, which of course is equal to the square root of 4 plus 16, or in other words, the square root of 20. And I'm going to simplify this square root, so I'm going to look for the largest square factor. And I'm hoping that you had a chance to do your homework, which was just to memorize the first, what was it, 13 perfect squares. So I see that 4 is a factor of 20. That's a perfect square. So this is going to be, well, the square root of 4 is 2. So this is 2 times the square root of 5, right? So that is what b is equal. It's 2 times the square root of 5, okay? And now I should be able to calculate the purple line, because I know that the yellow line, let me bring up the yellow line is 3 meters. So I should be able to calculate the purple line. So let's say that this is a. Let's say that a is equal to 3, b is equal to 2 times the square root of 5, and in purple, let's say that the hypotenuse is c, and c is what we're looking for. So again, we can use the Pythagorean theorem again to calculate the same thing. So let's do, so I know that c is equal to the square root of a squared plus b squared, and c is equal to, therefore, well, a is 3, so I've got 3 squared, plus b squared. B is 2 times the square root of 5, so I'm going to do 2 times the square root of 5 squared, like that. And this is equal to, well, the square root of 9 plus, well, 2 squared is 4. The square root of 5 is, the square root of 5 squared is 5, so we've got times 5. And so this is going to be the square root of 29. So that is what the hypotenuse is equal to. So this is, I think, a really cool question, because we have to use radicals a few times. Now I think it'd be good if we looked at what the actual formula is, because yeah, you know what, actually I don't think we do need to know the formula. I think that this amount of work is perfectly reasonable for this type of question. If you want to know the formula, I think that you can look it up. It's really not hard to find, but I think that it's actually good to do some of this work for yourself. Okay, I'm gonna do a couple more questions just from your textbook, and we'll take it from there. So let's say we're gonna do. Yeah, let's add and subtract some radicals. I think that this is a good exercise to do. So let's add. Let's do this one. Let's do the square root of 50 plus the square root of 3 times the square root of 2. 3 times the square root of 2. And this is from page 276 in your textbook. So if you're following along, this is on page 276. Okay, so there's a few ways that we can do this. I think that the most straightforward way of doing it is to figure out how to get this simplified, and then we'll see what happens. Let's simplify everything the best that we can, and then see where it goes from there. So I'm going to look at the factors of 50, which are perfect squares. So my perfect squares, if you recall, are, well, 1, 4, 9, 16, 25. Oh yeah, 25 is definitely a factor of 50, so let's pull out 25. The square root of 25 is 5, so this is 5 times. Well, 50 divided by 25 is 2, so this is 5 times the square root of 2, plus 3 times the square root of 2. And there we go. So now this is a lot like adding like terms. So remember, like, if I were to ask you what 5x plus 3x is equal to, you'd probably ask yourself, well, how many x's do I have? I have 8 x's. Well, it's the same thing over here. Like, if you want, you could just think of the square root of 2 as x, right? Because I'm multiplying 5 by that. Right? Because x in this case with algebra, like, x can be any value that you want. So in this case, like, all these rules that we have, as long as it's the same x, like this is like the square root of 2, we should be able to add them no problem. So 5 times the square root of 2 plus 3 times the square root of 2 is going to be, it's going to be 8 times the square root of 2. And that's all there is to it. That's the whole question. So if you wanted to, like, you could convert this into an entire radical by saying that this is going to be equal to the square root of 64 times the square root of 2, which is equal to the square root of 128. That would be fine too. But nowhere in the question did I ask you to to write it as an entire radical or a mixed radical or anything like that. So because this is already simplified, I'm going to say that we're done here. So this is simplified and we're done. Ooh, let's take a look at this one. This one's a little bit messier, but I think that's okay. So let's say this is also I guess the first one was part A. This one is part B. Let's do negative square root of 27 plus 3 times the square root of 5 minus the square root of 80 minus 2 times the square root of 12. So this one is pretty hairy, but I think it's fine. So let's see what we get here. So the first thing I'm going to do is I'm going to just simplify everything. Do I have a Discord? Yes, I do. I do have a Discord. You're more than welcome to join it. Let me just give you the link. Invite people, copy, and there you go. Yeah. So yeah, you're welcome to come join the Discord, and then if you want, you can ask a question with your voice. Although most people are pretty shy on the Discord, but you can also ask a question over text or what have you. It's also a good way to communicate with me as well. I think that Discord is probably my favorite way of messaging. I think I like it a little bit better than Instagram, although it's all really the same. Like if you have a question, you have a question. So. Okay. Anyway, back to the question. Let's simplify all of these. So let's write all of these in terms of a mixed radical. So really, what we're going to do is we're going to simplify it as much as they can be simplified. So in other words, I'm going to factor out all of the largest perfect squares that I can. So let's start off with this one. And this is what I'm talking about, how you really need to know your perfect squares off by heart. Like you can't make this up as you go along. You really do have to know these. Like I look at 27 and immediately I know that 9 is the largest square factor that I can take out of it. So when I take out a 9, I'm going to get negative, well the square root of 9 is 3, so I'll get square root of, or negative 3 times the square root of, well 27 divided by 9 is 3. So another 3 there. 5 is a prime number, so I can't factor anything out of that. So I'm just going to leave it as is. I've got 3 times the square root of 5 minus, well, 80. Let's think about the big factors of 80 that I can take out. 4 definitely works, but I think we can go higher than that. Well, let's think about 16. Can we take a 16 out of 80? Well, yes, we can. 16 times 5 is equal to 80. So I'm going to take out a 16. The square root of 16 is 4. So I get 4 times, and then what's left over is 5, because 16 times 5 is 80. Finally, let's look at the square root of 12. Well, I think the biggest one that we can take out of 12 is 4, right? Because the one after 4 would be 9. 9 is not a factor of 12. The one after that would be 25, and 25 is already bigger than 12. So we can't go anything bigger than 4. So let's factor out a 4. When I take out a 4, the square root of 4 is 2, and I have to multiply it by this 2, so I'm going to multiply that by 2. I'm just going to write 2 times 2, and what I'm left over with is the square root of 3. And just to be clear, this is a minus sign here. I'm going to make my operations look a little bit nicer. Okay, so we're definitely one step closer. What I'm going to do is I'm going to sort of group these together. So I'm going to put this guy beside this guy, and these guys are already beside each other, but I'll keep them beside each other. So let's worry about the purple guys first. By the way, this 2 times 2, I'm just going to change it right now to 4. I don't think there's any reason to keep it as 2 times 2. So I'm going to rewrite these so that they're all beside each other. So I've got negative 3 times the square root of 3 minus 4 times the square root of 3 plus 3 times the square root of 5 minus 4 times the square root of 5. Now, we have to think of these kind of like terms, just like we would in algebra. So what I mean by that is these square roots of 5, these are like terms right here. These are the same, right? We've got a square root of 5, we've got another square root of 5. So these guys are like terms. The other ones, the square root of 3 and the square root of 3, these are like terms. So that means that I can add these guys together and I can add these guys together, but I cannot add them all together all at once. So we are going to have some different terms to deal with. So we're not going to be able to simplify it all into one single term. It's going to be several different terms. So let's go ahead with that. So negative 3 minus 4, that's negative 7. So we got negative 7 times the square root of 3 plus, actually I should say minus, because 3 minus 4 is negative 1. So it's negative 1 times the square root of 5, or in other words, just negative square root of 5. So this one is done. So we've got negative 7 times the square root of 3 minus the square root of 5. So that's how this one that's how this one plays out. I think I'm gonna leave that one. Actually, no, let's do this one. I think this is a good one too. These are all good examples. I have to say, and I don't always say this, but I really do actually like this textbook quite a bit. These are really good questions. So let's do part C. We're going to do the square root of 4c minus 4 times the square root of 9c. And then they have a little disclaimer here saying that c is greater than or equal to 0. The reason they're saying that is they wanted to put a variable underneath that radical sign, but they know that if we're taking the square root of a variable, the variable definitely has to be greater than 0. If it's negative, then we'd be taking the square root of a negative number, and we know that there's no solution to that. So they are explicitly saying c is greater than 0. So let's take care of this. So again, I'm going to simplify this, and I'm going to simplify that, and I'm going to see what's left over. So I've got the square root of 4c. Well, 4 is very conveniently a perfect square, so I'll remove that. And when I take it outside of the square root symbols, I have to take a square root. So the square root of 4 is 2. So I'm left with 2 times the square root of c minus 4 times, well, 9, which is inside the radical sign. It's part of the radicand. When I take that outside of the radical sign, I have to take its square root. So let's go ahead and do that. Square root of 9 is 3. And I'm left with the square root of c. Now, obviously, I can't take the square root of c because I don't know what c is. C is just c. So I can't really do anything with it. I'm going to clean this up because 4 times 3 is 12. So I can clean that up a little bit. So I'll write 2 times the square root of c minus 12 times the square root of c. And finally, let me just give myself a little more room here. Finally, we just add these as though they are like terms. So let's go ahead and do that. 2 minus 12 is negative 10. So I've got negative 10 times the square root of c. And that's that question. We're done. Yeah, I really like that question because we've got some variables in there and we're kind of sneaking in a variable without changing the parameters too much. And then I'm gonna do this last question here, and I think we're gonna call it a day. We'll end just a little bit early today. So let's do this example here. So this is an example from page 277, and it's a really cool question. I really like it. So this is page 277, and I highly recommend you to get your book and actually take a look at this question. I mean, I'm going to write it out anyways. In fact, I think I did this earlier, right? I think I took a picture of it. I'm gonna do that again. So let's see here. I'm just going to click this, and here we go. So here's my oopsies. Okay, here is the question here. There it is. So I wonder if, can you guys even see that? Yeah, oh yeah, you can. You can definitely see that. Okay. Okay, so gonna just take a little snapshot. Gonna use it, and oops, no, I don't want to do that. I want to crop it. Crop. There we go. And just like that, now we've got this question in my program. Great. Look at that. Beautiful. Okay. Sometimes I wonder if, like, I'm always tempted to do things like the neat way, but I wonder if that actually saved any time. Oh, uh-oh. What went wrong here? Ah. Can you guys see that now? Am I back? Okay, yeah, my HDMI cable got unplugged. Okay. Yeah, okay, so let's take a look at this question. So we're going to apply addition of radical expressions. So we've got a, oh, you know what? Oh, shoot. Yeah, you know what? We haven't, because we skipped the trigonometry section. So you know what? We're actually going to skip this question. Oh, that's too bad, because this is a really good question. So I guess, yeah, because we did skip the trigonometry section. We still have to come back to it. Oh, what a bummer. Yeah, we'd be using SOHCAHTOA for this one. Shoot. Oh, what a disappointment. Just hold on one second. I'm gonna pull up a different question, one that's not in our textbook. Yeah. Okay. You know what? I'll just get one from the exercises. That's disappointing. I forgot that we hadn't done trigonometry yet. So maybe that's a sign that maybe after this we should head back and do some trigonometry. Let's see, I'm just trying to find a good question here. Okay, yeah, let's do one of these ones from the exercise. This is on page 279. So I'm gonna delete that. Page 279. Oops, 279. And I'll do the same thing again with the camera. Excuse me. And picture. There we go. Sorry about that, guys. Okay, let's do. Yes, this one here. Okay. And just want to make sure that the HDMI cable didn't get unplugged there. Looks like it's okay. Okay, so now I'll crop this, and we'll do maybe just one of these, and then we'll call it a day. So we're going to express each pair of terms as like radicals and explain our strategy. So what this question is saying is, like, okay, so we've got like we've got a whole bunch of terms underneath each of these radicals. So let's start off with this one here. So we've got some terms underneath the radical. Like this one here has a 5 underneath the radical. This one has a 125 underneath the radical sign. So is there any way of making it so that these have the same radical? Is it possible to do that? Well, yes, it is possible. So we're not gonna change this first one. This one you can't really do anything with 15 times the square root of 5, because 5 is a prime number. So not only does it not have any square factors, it doesn't have any factors except for 5 in itself. So the only way that we could get the 5 outside of that radical is if 5 was a perfect square, which it couldn't be because it's a prime number. So that 5 has got to stay put. So this first one, we got 15 times the square root of 5. And then the other one is 8 times the square root of 125. Well, certainly we can take some stuff out of that. So let's go ahead and do that. So we're thinking of the largest square that we can take out of here. So I'm thinking we could take out a 25. And when we're left with that, well, we would take out the square root of 25, which is 5, and we would multiply that by 8. So we would get 40 times, well, 125 divided by 5 is 5. So, and now look at this. Now these are both of these are like radicals. So what I mean by like radical is two radicals that you can add together because they have the same radical portion. So this is, they've got the same radicand. So underneath the radical symbol, they have a 5. So that means that we can add them together. If we wanted to add them together, we could say 15 times the square root of 5 plus 40 times the square root of 5 is equal to 55 times the square root of 5. We could add them no problem. So these ones we can now add together. Let's do part C, and then I'll leave B and D to you guys. So let's do part C. So part C I'll do over here. I've got negative 35 times the 4th root. Ooh, scary 4th root. W squared. I guess I don't need the radical to be that big. Okay. And so that's one of them. The other one is 3 times the 4th root of 81w to the 10. Whew. 4th roots, isn't that spooky looking? Okay, so it doesn't look like we can do anything with this first one because we're taking the 4th root of w squared. So if I take the 4th root of w squared, if I was to take out anything from that radical, it would have to be a power of 4, and there is no power of 4 here. The only power that we have is a power of 2. So remember that if I were to take like the nth power of a to the power of n, that would just give me a back. And if n was even, then we may have to think about the absolute value. But in any case, we don't have a power of 4 here. We only have a power of 2. So that means that we're going to have to just attack the second one. So let's go ahead and do that. So let's see if we can take anything from this 81. So this 81, let's see if we can write that like as a prime power composition. So in other words, let's see if we can factor this completely. So I know that 81 is 9 times 9, and 9 is 3 times 3. These are perfect, these are prime numbers. So it looks like 81 is equal to 3 to the power of 4. Perfect. Now let's think about w to the 10. Let's see if we can split that up into powers of 4 and see what's left over. So I would have w to the power of 4 times w to the power of 4 times w squared. Right? And that's what w to the 10 is, right? Because I've got 4 plus 4 plus 2 is 10. So if I wanted to rewrite this, what I could say is that this is 3 times the 4th root. The 3 is coming from here. It's just on the outside. Times the 4th root of w to the 4 all squared, right? Because I've got 2 of them. That's what that is. Times w squared, that's that. Times 3 to the 4. Times 3 to the 4. Okay, and this is getting a little bit messy, so I'm going to erase some of this stuff. If you need to see what it is, you can go into YouTube and rewind and pause and stuff like that. And this looks like a 34. I want to make absolutely clear that this is 3 to the power of 4. And I'm going to rearrange a couple of these things. I think what I meant to say here, so this is 3 times the 4th root of, I meant to write over here that, first of all, I wanted the 3 to the 4 to come first. So that's actually coming all the way over here like that. The next thing I wanted to write is, it wasn't so much that it was w to the 4 squared, but I wanted to actually write w squared to the 4. And you'll see why I want to do that in a second. all times w squared. Okay, so I just sort of rearranged some of the terms. I think it's important to know that you know, a to the b to the power of c, that's equal to a to the power of c times b. So if you're not sure why, feel free to ask. Basically, this is just one of our exponent laws, because this is equal to a to the power of b times c, and multiplication is commutative, right? You can change the order of multiplication without actually changing anything. Anyways, going back to this question, I'm going to say this is 3 times, well, if I take the fourth root of 3 to the 4, that gives me 3. So I'll write another 3 here. Now, if I take the fourth root of w squared to the power of 4, that gives me w squared. And all that's left in the brackets, in the radical, is the fourth root of w squared. And let's clean this all up. So this gives me 9 w squared times the square root, or sorry, the fourth root of w squared. And that would be it. That's that question. Because now look at this. We have this guy right here. That's what we solved for. And this guy, and now these are like radicals. We could add them together because they both have a w squared underneath that radical. So their radicand is exactly the same. So really all we did here was just simplify it, and that was our strategy. So if we want to talk about strategy here, because it does ask us to explain our strategy. If we want to talk about strategy, our strategy here was just to write both of our expressions into lowest term, or not lowest terms, in simplest terms. So we simplified our radicals. So in other words, we were writing them as a mixed radical. Okay. So I think I'm going to end it there. I know that we have a couple minutes left over, but I'll give you just a little bit of extra time to try some of these questions on your own. If you have any questions about how things are going or what our plan is going forward, don't hesitate to reach out and contact me either on Discord or Instagram or YouTube or email, whatever your favorite way of contacting me is. Go ahead and do that. Otherwise, I'm going to leave you with some homework. I'm going to put those page numbers and stuff on the website. I may as well also write them out now. So I'll just write your homework now, and then I'll also put a note on the website for your records. So the homework is going to be page 278, and we're going to go from numbers 1 to 10. And I'm going to throw in a few of the sort of longer answer questions. I like the number 11, and I also like the number 13, and I'll do one more. Yeah, I like number 22. Number 22 may cause some problems. So definitely try all of these. And as I usually say, and I should probably be emphasizing this more and more now that we're doing these online classes. If you get stuck on a problem, like don't get discouraged. What I want you to do is just circle the problem or make a note of it and then bring it up and bring it to my attention, and that gives me something to work on with the class, because it's really helpful to actually like see the thought process being done. So if you do have a question, bring it to me. Tell me, say, oh, you know, Mr. Bennett, I couldn't do question number 22. I was stuck, and then I'll do it next time we see each other. So yeah, definitely give these a try. I think that we only have a few more sections of chapter 5, because it's one of the shorter chapters, which is I think 5.3 is the highest one. 5.3. So we just finished 5.1. We'll do 5.2 tomorrow. I think that 5.2 is actually more straightforward than 5.3, but we'll see. And then 5.3 is about like equations and stuff. So it should be kind of fun. And look at that. They've got, oh, this is so cool. Here, I'll show you. I mean, you can see it for yourself, but it's a skate park in Calgary. I've been there. I skated that when I was a kid. I think I was like 13 years old, and my dad took me. We went on a road trip to visit some relatives, and there's Millennium Park, and they resurrected, or not resurrected, they erected the park in, I think, the year 2000, which is why it's called the Millennium Park, and it was a world class skate park, and the whole world was aware of it. Even in the skateboard magazines and stuff, they featured this park that was in Calgary, and it was pretty cool because all the Canadian skateboarders were like, "Hey, look, we're on the map." And then I got to skate it, and honestly, it wasn't as fun as I thought it would be. It was kind of not the best part. I mean, it was really good, but it's kind of like some skate parks are meant for like people who are like really really good and can do like big like half pipes and stuff like that, and that's not who I am. So it was kind of just like skating any other skate park, because I just ended up doing kind of the smaller things. But yeah, it's kind of cool to see a place that I've been. I have a feeling that there's a skateboarder or a snowboarder who was on the list of authors here, because there's an awful lot of questions about skateboarding and snowboarding, which I think is pretty sweet, because it's fun to see some representation of people who like to have fun with outdoor sports and things like that. Yeah, anyways, I really like this textbook. I think honestly, of all textbooks that I've had to use in my teaching career, like this one is probably like the best textbook that I've worked with. So yeah, I'm really fond of this book. Anyway, I hope that this helped a little bit. I know it was kind of like just sort of one example after another. But I like to do that every now and again, just have these sort of workshops. And again, I'm still learning how to do this online stuff too. So if you have any suggestions about how you would learn in a more efficient way, or if there's something that I'm doing that doesn't really work very well for you, obviously be polite about it, but let me know, and I can make some adjustments. Like if you want like more of like a theoretical perspective, where I'm kind of just giving you notes and like background and theory, I could do that. I kind of like to think that the best thing for us right now is just examples and examples and examples, because that's what I want you to be doing, and it's really helpful for you to have those examples. And the theory is all in here. Like you can read through the book if you want kind of like an explanation of how this works and some of the deeper understandings that you might get. But I think what I can provide you is like hands-on examples, because we're kind of robbed of that due to the current situation. So but yeah, again, if you have any suggestions, please don't hesitate. I'm not going to take offense unless you're like super rude about it and you're like, yo, you suck and I hate everything that you're doing. I'll take offense to that. But if it's just like, if you have some constructive criticism, I'd love to hear it, because I want this to be as good as possible for everybody. This is not about me. This is I'm not trying to fulfill some kind of weird desire or something, right? Like we're just stuck here. So this is all about you. So if you have any suggestions about how we can make this work better, I'm glad to hear them. But in any case, I'm gonna sign out now, and I'll talk to you guys tomorrow. I'm gonna be here at the same time. Just a couple things. I think more and more people are handing in the assignment. If you like, I don't know, like I feel like my reach, I've got about a 60 or 70% reach of my class. So I'm thinking that like there must be some students who either, I mean, maybe they're just ignoring me, but maybe they just don't have access to their email or something. So if you know someone who is who's still around and maybe they're just kind of out of the loop, maybe just send them a quick message and say, oh, like I had noticed you're not watching the live stream or something like that. Maybe it would help if it came from a different student, because it would be nice if we could have more students, right? Because the wider my reach is, the more successful everyone is going to be. So yeah, definitely, like if you can think of anyone who might not be tuning into all the broadcasts, then maybe let them know that it's super awesome and fun and we're having a great time, because that'd be great. Anyway, I'm gonna sign out now, and I will see you guys tomorrow. Okay, bye-bye. Bye-bye. Oh, okay. Oh yeah, I gotta close off YouTube now.